Thank you so much for inviting me and for having me here. It's a great pleasure, as always, to be back. This is my first in-person seminar since everything started. And I'm very happy about the work that I'll be telling you about. So let me start with a brief overview of the main results. I'll be telling you about how we've constructed n equals 1 supersymmetric ADS4 vacua in compactifications of type 2b string theory on orientifolds of Calabi-Yau hypersurfaces in toric varieties. And the vacuum energy, excuse me, while I close the window. The vacuum energy that we find is exponentially small. In fact, in some cases, it's smaller than the observed vacuum energy in our universe, although because this is ADS, the vacuum energy is negative. But the internal spaces are not huge. They're, say, a few thousand string length to the sixth in volume. And another, to me, striking qualitative point is that the cost of the search is not of order 1 over the vacuum energy that we find, much cheaper than that, rather. The underlying mechanism is a racetrack superpotential of type 2A Worldsheet instantons on the mirror of the space on which we compactify to B. That turns out to cause modest integers, Gopa-Kumar-Vafa invariance and flux quanta, to be combined in an exponential way to give the vacuum energy. So as an example, we find cases in which the GV invariance 2 and 252 show up, and because of a choice of flux quanta, they end up being raised to the power of 58. And this gives a very nice small number. Now, these models are not realistic. The vacuum energy, first of all, is negative, although the KK scale is quite high. Some moduli are ultralight. If one indeed makes the vacuum energy of order the observed scale, then some of the moduli will have masses of order the present day Hubble constant, 10 to the minus 33 electron volts. Now, it is possible, I think, to take these constructions and uplift them to de Sitter vacua. But the de Sitter vacua that could result from these constructions themselves would still have ultralight moduli. And so they would not in any way look like our universe. All the supersymmetry breaking scales would be very low. And so these constructions, although I think they're interesting, do not help with the real CC problem, which is, of course, to get small cosmological constant after supersymmetry breaking at a substantial scale. What they do is solve what you might call the supersymmetric CC problem, which is to show how you can get an exponentially large supersymmetric universe in a theory with a small fundamental length scale. They also change at least my own picture of how accessible such kinds of solutions are in the string landscape. Okay, so now a brief technical summary. What do we actually do? We find quantized fluxes for which the expectation value of the Kukov-Alpha-Witten flux superpotential is exponentially small and the string coupling is polynomially small. The nonperturbative superpotential arises from rigid prime toric divisors with constant Pfaffians. I'll define what all those things are. All the tadpoles are canceled, all the moduli are stabilized. We explicitly include Worldsheet instanton corrections to the Taylor potential to demonstrate the control of the construction. And to do this, we relied on a whole bunch of new computational tools for computing GV invariance, for orientifolding, uplifting F theory, and for enumerating Euclidean D3-brane contributions to the superpotential. And all of these things at large Hodge numbers. So that's where we had to make some technical progress. I won't spend a lot of time talking about the technical progress. I'll mostly talk about the actual constructions. So this was done by some outstanding collaborators, my former students, Mehmet Demirtas and Manki Kim, now postdocs, current postdoc Jakob Moritz, and current student Andres Reyes-Tesco. And we have a collection of works on this. The main work on this came out in July, and we have more things coming. There's been some attempts and achievements in other directions by other groups in recent months. Okay, so just to make sure that the forest is visible, our broader goal is to try to compute parts of the string landscape and to understand, by enumerating them, which kinds of low energy quantum field theories are possible in quantum gravity. And we'd like to construct ensembles of vacua whose cosmological and particle phenomenology we can study. Okay, so the plan of the talk, first I'll explain how we got an exponentially small flux superpotential. We'll combine that with Euclidean D3-branes to find supersymmetric vacua, and then I'll argue that we have control of alpha prime. So first, a review. The KKLT scenario for de Sitter vacua. which is the framing for this work. So Racetrack, Lende, and Trivedi in 2003 suggested that one consider a compactification of type 2b on an orientifold of a Calabi-Yau threefold that includes quantized three-form flux, an n=1 supersymmetric pure super-Yang-Mills theory on some 7 branes, wrapping a divisor in the threefold, a Klebanov-Strassler throat region containing 1 or more anti-D3 branes. And then the claim of KKLT is that in a suitable parameter regime, these sources can be combined to yield a metastable DS4 vacuum, and corrections to all the approximations are small. Okay, so this is the recipe, and one would like to understand whether one can find the ingredients for this recipe and then actually cook the dish. Now, we won't be talking about de Sitter today unless there are questions. What we'll be doing is anti-de Sitter vacua, supersymmetric anti-de Sitter vacua, and for that purpose, we can afford not to include a conifold region or anti-D3 branes. Claim of KKLT for these ingredients, quantized three-form flux, super Yang-Mills on 7 branes, is that in a suitable parameter regime, these yield supersymmetric ADS4. That's our goal, to achieve constructions like this. As you'll see, our constructions have some slight variations compared to the original idea, but they're in this framework. Okay, so a little bit more detail about the setup. The moduli in question are the axiodilaton, H21 complex structure moduli, which I shall call Z, and H11 Kähler moduli, which I'll call big T. So suppose I pick some quantized fluxes, F3 and H3, quantized three-form fluxes. We'll combine them to form a complex G3 flux, F3 minus tau H3. And then the 4-dimensional n=1 supergravity is characterized by flux superpotential of the form integral G wedge omega, where omega is the 3-0 form of Calabi-Yau. And a key result in flux compactifications is that if one makes generic choices of G3 flux, the solutions of the F-term conditions for the axiodilaton and the complex structure moduli are isolated. So in this sector, the complex structure and axiodilaton sector, the supersymmetric solutions are isolated points. There remains a Kähler moduli space at this level. And so suppose now we look a little bit below the scale where those moduli, the complex structure moduli, have acquired a mass. The effective theory has, in the approximation that H11=1, which is for pedagogical purposes only, the actual constructions have more. The Kähler potential is just minus 3 log of T plus T, where with T the overall Kähler modulus, describing the volume of the space. And since the complex structure moduli have gotten vevs, I can evaluate integral G wedge omega on their vevs. That's what those angle brackets mean. And we'll call the thing evaluated there W naught. Now, in this theory, suppose we consider a stack of D7 branes that support SU-NC super Yang-Mills with no matter. Then at low energies, that theory generates a gaugino condensate superpotential. And so the total superpotential is the sum of the constant term for fluxes, and then an exponential from the 7 brane gaugino condensation. Here A is a Fathian. It's a fluctuation determinant, which we'll come back to. Now, if you take this supergravity theory given by this Kähler potential and this superpotential, then it's a fact that it has a supersymmetric ADS4 minimum plotted here, and you can solve for it easily. And the key point is that that minimum occurs at large values of T, where the alpha prime expansion is under control, if and only if W naught is small. Okay, so the core point is one needs to find that the expectation value of the flux superpotential on the vevs of the complex structure moduli is extremely small, in fact, exponentially small. And then the minimum of the Kähler moduli potential will occur at large volume and everything will be under control. So that was the fundamental claim. Now, in the paper of Racetrack, Lende, and Trivedi, they just said, well, small W naught should be possible. I'll show you how it's possible. I'll give you a construction. Okay, now the statistical argument that one could make and was made is that small W naught is not generic, but anyhow, there are exponentially many choices of three-form fluxes. B3 is the third Betti number. There's some of order e to the B3 choices, and some of those choices ought to give small W naught. And the challenge has been finding choices that in fact do give small W naught. Now, what one should ask is, well, do there exist consistent compactifications that have quantized fluxes giving an exponentially small classical superpotential that at the same time have suitable gaugino condensates or Euclidean D3 branes, which generate the same kind of superpotential term? And the answer to the first is yes, we give a construction of this a couple of years ago, and now also yes to the second. And this suffices to construct explicit supersymmetric KKLT vacua, and that's what this talk is about. What you could do though is, okay, let's draw a line and talk about something that won't show up in this talk. You could also put conifolds in these solutions. We can find points in the moduli space where there's a Klebanov-Strasser throat region. We haven't done that because to really make use of that, one needs to be able to analyze supersymmetry breaking from antibranes. And that's a different kind of story. We wanted to completely lock down the foundations by studying the superpotential first. So that's today. But I don't know of any obstructions actually to adding conifolds. We just haven't done it. So I gave a talk summarizing the status of de Sitter constructions at Strings 2019, the last place I saw many of you, in fact. And my slide from that summarizing the status was there was no evidence of any obstructions, but we were still awaiting complete explicit compactifications. And I claim that for ADS, we have now given them. And DS is absolutely a work in progress. Okay, so the rest of the talk is explaining the sense in which we can actually put a check mark there. Okay, so the general argument is that small W naught should occur, but exponentially rarely. And preferentially, it'll occur when the moduli space dimension is large. The old argument due to Bousso and Polchinski is that one should think of picking integer fluxes in a high dimensional lattice. So we have some computational tools that could allow us to explore those kinds of moduli spaces, but brute force is still super challenging. And so the best people could do in the past was W naught of order 10 to the minus 2. But remember, you have to take a log to get the expectation value of the moduli. So it's still not so great. And it's better to use a mechanism a bit different. Okay, so any questions about the overall status before I go into actually explaining how we get small W naught? Okay, so start with the picture of a racetrack. The idea is to use a racetrack. What is a racetrack? Suppose you have a superpotential that depends on one variable z. And suppose the superpotential has two terms, both decaying exponential. So P1 and P2 are some positive numbers, and N1 and N2 are two numbers. Well, clearly this potential goes to, superpotential goes to 0 as z goes to infinity along the real line. But if N1 and N2 have opposite sign, then you can find a minimum, the supersymmetric minimum that results from this superpotential. You can evaluate the superpotential at the minimum and find that it's given by an expression like this. So all I've done is minimize this function of a single variable. The point, though, is that the value of the superpotential at the minimum is small if the exponent is a large number and the thing in big parentheses is a small number. And those are things that are given in terms of the inputs N1, N2, P1, and P2. And field theory, this is a very old idea. I should stress that the supergravity theories that I'm going to tell you about today, once we go to the low energy effective theory, could well have been written down. Maybe, in fact, people thought of them in the 80s. But there's something added in showing that they actually arise in string theory. That's where we're doing this. So what we need to show is that in a bona fide solution of string theory, in fact, the superpotential, the flux superpotential does take that form with the exponents very close to each other and the prefactors hierarchical. So we'll do that. Okay, so one slide with notation and calculation. So suppose I've introduced a symplectic basis of H3 of my space X. Then I can write the periods of the 3-0 form in terms of integrals over that basis. Here, Z's are coordinates, homogeneous coordinates on the moduli space, and FA is the derivative of the prepotential with respect to those coordinates. When I leave out the 0th one, Z0, then I'll have coordinates ZA, of which there are H21. So the periods are the basic data here. Now, the prepotential can be written in terms of a polynomial part and an instanton part. The polynomial part has a cubic, quadratic, linear, and constant, and it's determined in terms of the intersection numbers and Chern classes of the mirror. Details don't matter much to us right now, but we know it. One knows what it is. And the instanton part is also knowable. It consists of a sum of Worldsheet instantons, actually conveniently expressed as trilogarithms of exponentials of, so Q is a curved class and Z is a vector of complex structure moduli. And the coefficients n sub Q tilde. Every time in this talk something has a tilde, it means I'm working on the mirror. Okay, so these are Q tilde in M of X tilde. That means Q tilde is a curve class in the Mori cone of the mirror threefold. And N sub Q tilde are the genus 0 invariants of the mirror X tilde. Okay, so far, if you put these things together, you see that I could compute the periods of the 3-0 form in terms of the polynomial and instanton terms. But what does this have to do with the flux superpotential? Well, the flux superpotential, I said it was integral G wedge omega, but one can actually write it as a symplectic pairing of the vector of periods with the symplectic matrix sigma over there and a vector of fluxes. So if I know the periods and I choose some integer fluxes, I can evaluate the flux superpotential. But in particular, okay, here's the key point from this slide. All the rest was set up. The key point is that the flux superpotential can be decomposed into a perturbative part and an instanton part.
Explain why the polynomial part truncates the cubic?
Yeah, it's non-normalization. So it's a this one here is the chi, the zeta of 3 is the last loop correction. Right, and that will actually be important because we're going to need to work with that polynomial part, and we need to know it exactly. But conveniently, it's not renormalized. Good, other questions? Okay, now this decomposition, why do I care about the decomposition? So what do I mean by pert and inst here? W flux pert is the part that you get if you evaluate pi sigma flux using the perturbative contribution to the periods, that from this. And the instanton part is everything else. And what we're going to do, here's our idea. We're going to find choices of integers f and h such that the perturbative part of the superpotential is identically and exactly 0 along one complex direction in the moduli space. We call that a perturbatively flat vacuum. Then we're going to find cases in which along that perturbatively flat vacuum, the remaining contributions to the flux superpotential, which are only instantons, take the form of a racetrack. In that case, the full flux superpotential is only all the constants are gone, all the perturbative parts are gone by choice, by an exact choice, because we're only working with, so note that the objects in F poly are just some integers that we know. I didn't tell you exactly how to compute them, but they're given in terms of the intersection numbers and Chern classes. So when W pert exactly vanishes, all that remains is W instanton, and then the whole superpotential is exponentially small. So here's an example. We'll study a Calabi-Yau threefold where H21 is 5, so 5 complex structure moduli, 113 Kähler moduli, which turns out to be a lot. When we find quantized fluxes, here they are. Here's our choice of fluxes in a symplectic basis. The symplectic basis has two H21 plus 2 elements, so 12 things here. Such that there's a direction. Here's a direction, P, look at that vector. Such that along a particular direction in which Z, the complex structure moduli, and tau, the axiodilaton, are proportional by this rational vector. That is a perturbatively flat vacuum for this choice of fluxes. Along that direction, the perturbative flux superpotential exactly vanishes, and all that remains are the Worldsheet instantons. You can think of them as 2A Worldsheet instantons, although of course we're compactifying 2B. If you know how to compute them, then you can figure out which ones are the leading ones along that direction. And they have GV invariance -2 and 252. So then when you evaluate the full flux superpotential, all it is a sum of exponentials. Some constant, it doesn't matter, but that we know, 2 exponentials, and then a term that's something in. So you can ignore this. Let's look at the ones in red. Opposite signs, please.
Those terms came from different instanton numbers?
Yes, those are different curve classes. Yes. Yeah, they're the
exponents are amazingly close.
Yes. Yes. In fact, this is exactly where we add value, because if one had written down a racetrack of this form, let's say right after the KKLT paper and said, you can make an arbitrarily small CC by making a racetrack of Worldsheet instantons on the mirror, I, for one, might have said, that's absurd. I don't believe that you can necessarily tune that. But what we looked into, I don't say that every Calabi-Yau threefold we looked at had this property, but we found some that do. So, and indeed, that's the goal, to make those exponents quite close. 729s and 728s. Well, when you minimize that, so yeah, -2 and 252 are 2 different curve classes. And when you minimize that flux superpotential, well, W naught is 2 over 252 to the 29, which is 10 to the minus 62. G string is only the log of that. So G string is still small, but it's 10 to the minus 2. Okay, so this is the core example, actually. Questions about this example?
To what extent does W flux depend on the other 4 moduli? Because tau is one of your 5 complex moduli, is that right?
Yeah, so what I did is I wrote my flat direction in terms of the axiodilaton, because along this is a flat direction in the joint complex structure moduli, comma, axiodilaton moduli space. So actually, even though there's 5 complex structure moduli, this is a direction in a 6-dimensional moduli space. And so if you see it here, actually, W flux is just a function of tau now along that line. And off that line, it's quite steep.
But you pick your direction in that complex structure moduli space based on, achieving this particular.
So what you do, I mean, if you wanted to think of it as a random process, you choose integer fluxes and ask, is there a perturbatively flat vacuum? Almost never.
Yeah, and so the P, it minimizes the superpotential with those fluxes.
This vector P has the property that with those fluxes, the perturbative part of the flux superpotential identically vanishes along the vector P.
But it also therefore minimizes.
Yeah.
Is that obvious?
This is so at the totally perturbative level, if you don't include the Worldsheet instantons, along the vector P in the moduli space, it's flat, just flat. And away from the vector P, it's curved upward steeply because of the fluxes.
So how do I know that it's always curved upwards?
Well, one does want to actually compute the Hessian, but what we've done is solve F flatness conditions.
Okay. So the choice of P is determined by the F flat condition.
Yeah. So when I say there is a perturbatively flat vacuum, I mean there exists a choice of fluxes such that when you try to find a minimum, you find a one complex dimensional line of minima that is exact at the perturbative level and is only lifted by the non-perturbative effects. So that's what we're living off of. Once you've made that, you can just have a racetrack happen along that totally flat direction. And then a point that I'd like to make now, in case it causes confusion later, as you know, there are perturbative corrections to things like the Kähler potentials. But remember that the F-term potential goes to 0 if W and its derivatives go to 0. So since W is small, no matter what kind of corrections I get to the Kähler potential, unless they invalidate the whole construction, they're not additive. They're multiplicative. Yes, Juan?
So tau is 1 over G string squared.
1 over G string.
1 over G string. So these are different instantons.
Oh, thank you. They are these are not, you're thinking of D minus ones, right? D is of Euclidean D minus 1 branes or something. These are not Euclidean D3 branes yet, nor are they Euclidean D minus 1 branes. These are Worldsheet instantons of 2A on the mirror.
I would have expected a Worldsheet instanton to have an exponent that is independent of tau.
Well,
String coupling.
well, the Worldsheet, okay, so the Worldsheet instantons, if you were looking at Worldsheet instantons in, say, 2A, right, you would expect it to be e to minus 2 pi t.
Yeah.
But if you were expressing it in terms of the complex structure moduli of the mirror, it would be e to the 2 pi I u or something like that. Or in my notation, e to the 2 pi I z. So what I'm doing is I'm expanding around large complex structure. And so the pre-potential, for example, looks like cubic in z, quadratic in z, plus ... plus e to the 2 pi I z. And then I picked a direction where z and tau are proportional by numbers. So this is somehow relating the expansion around large complex structure to the expansion around weak coupling. Does that address the question or concern or not?
I thought that mirror symmetry relates these Worldsheet instantons to corrections to the flux superpotential.
Yeah, those are these.
Corrections to the prepotential.
Precisely. So right here. So these things. So here I've written everything in terms of, okay. So these are the z's of
that are corrections that would be computed just in ordinary gravity, right? If I'm mistaken.
which things could be computed? Which corrections do you mean could be computed in this?
Isn't this mirror symmetry usually used to compute the Worldsheet instantons in 2A by computing the?
Yeah, that's how we're going to do it for sure.
But in that language, they have nothing to do with difference.
Well, one way of saying it is that okay. Perhaps the way that I'm talking about in terms of 2A instantons is confusing. The calculation of the complex structure side of 2B is exact, and that's what's being used. And that doesn't need to come from some expansion in instantons. However, it involves things that are polynomial in the complex structure moduli and exponential in the complex structure moduli. And by trading those exponentials in the complex structure moduli for exponentials in Kähler moduli of the mirror, you get the usual Worldsheet instantons. I'm just using that language to explain why these things are exponentials. But if you like, all of this could be viewed as being computed purely classically by understanding the monodromies around large complex structure in 2B.
My only confusion was about the dependence on the string coupling, but maybe I can continue.
But I thought you were saying that if you go to your next slide, that you could equally well write those things instead of and with an e to the 2 pi I tau with the e to the I z instead. True. With no tau there. True. And it's just that you happen to be going along a flat direction where z and tau are proportional to each other.
That's exactly right. So in that sense, these things don't have to be morally 1 over G string. However, the perturbative flatness condition does link the complex structure moduli. So what we're doing is we're going along.
Is that the answer to your question, one?
Yeah, that answers my question.
Yeah, thanks. Good. So we're going toward LCS, large complex structure, at a rate that's prescribed by this vector P.
I mean, your computation of it has a z in it.
Yes.
And then you're just shoving z equals p tau in order to make it.
Exactly. I walk toward recoupling as I walk toward large complex structure, and that's why it ends up being G string dependent.
And
now, however, these things, sorry, go ahead.
Sorry, go ahead.
You might have thought, and this is what I thought you're asking, wait a minute, aren't there things that go to like e to the 2 pi I tau? Sure there are, including e minus 1 brains. And so what we'll have to do is check that those are subleading to this, and they are. Okay, so we have a superpotential that can be stabilized at a small value, so that's sort of fun.
So can I ask, your internal volumes are also like 100 or something, or smallish?
Right.
What's the volume of the Calabi-Yau is also?
What's going to happen in the end is the volume measured in Einstein frame, namely without factors of G string, of the total space. In this example, we'll do that 10 to the 5.
Okay.
And the 4 cycle volumes would be like 20 and 6 times 20, depending on whether it's Euclidean 3 brains or some combined group. However, string couplings 10 to the minus 2. And so the volumes measured in string frame, namely with factors of G string, will be confusingly small. And so that's where we have to do some work at the end to convince ourselves and you that actually we understand the alpha prime expansion. Luckily there we'll be able to do a direct calculation. I hope you'll agree that it's controlled, but there's some potential jeopardy. It's not yet a slam dunk until,
well, your problem in the direction of volume being too small, not big.
For sure. Right. Yeah, one will have to worry about that. We'll have a direct computation, but it's an issue that isn't obvious at all at this point.
Yes. Are you going to say how you found this example?
Yeah. In fact, perfect. Let's do that. How do we actually do it? So where does this come from? So okay, what's the process? Suppose you want to find a bunch of examples, right? You want to start with an orientifold, compute the prepotential, so you have to be able to work out the mirror map. You want to find some fluxes that align with the GV invariance in such a way that they give a perturbatively flat direction with a nice racetrack. And that third step is a search in a lattice, because you're trying to find some integers. And the dimension of the lattice is twice h21, so 10 in this example. It's not impossible, but it's sort of annoying to search in the 10-dimensional lattice. So it's a Diophantine problem, but it's not a Diophantine problem in a horrendous case yet. That's feasible for h11 up to maybe 5 on a laptop. We found this one on a laptop. You can find it pretty quickly on a laptop. You can go maybe to 10 or h21 of 10 or something on a cluster. I think if we worked for another month, we could probably go much, much further by using different methods. But the methods we use, you can get up to 10. Now, how do we actually do it concretely? So just a quick sketch of this, because in a sense, this is what we've been doing for the last couple of years in order to build up to this kind of thing. We're going to work with mirror pairs of hypersurfaces in toric varieties. So x and x tilde are mirror threefolds. V and v tilde are toric varieties related to each other. And then there's 2 coordinate polytopes that define those toric varieties. Kreitzer and Scarp have classified the four-dimensional reflexive polytopes that give nice toric varieties with nice mirror symmetry, and one just needs to find triangulations of them and construct Calabi-Yau threefolds as a result. We proved that the number of Calabi-Yaus that can result from the Kreitzer-Scarp list is at most 10 to the 428, but that's going to be plenty. So what do you want to compute? You want to compute all this stuff, this list of all these things, right? And I'm pleased to say that a software package that my students Mehmet Demirtas and Andres Tascon have written is easily able to compute all of these things. I won't go through them one by one, ask me if you want. Green is stuff that was already in the publicly released version of CY tools, and then blue is stuff that we'll release as soon as we can test it properly. So now we can easily triangulate for any H11 you might want. We can get the GV invariance up to maybe 100. I'll show you some at the end. Okay, here's the famous plot of Hodge numbers of Calabi-Yau threefolds. A hypersurfaces in toric right is H11 on the x-axis, H21 on the y-axis. And the labels say that the complexity of analyzing x grows exponentially with H11 and of x tilde with H21. And if you remember, I said you can only search for flux vacua for H21 up to maybe 10, so that's the green band. And the purple band is where if you take off-the-shelf software, good stuff like instanton, you can get the GV invariance. And unfortunately, those things don't overlap. So what we did is we developed the capability to compute the GV invariance pretty much everywhere. And then they overlap. And the sweet spot is where the search for flux vacua lines up with a lot of dots that we can compute. But if you look carefully where those dots are, you see that when we can do the search for flux vacua, when we can do this lattice search, the number of kilomoduli is pretty big, like order hundreds. The example I gave you, it was 113. And so we have to do everything, the whole story of flux compactifications at large H11, orientifolding, finding rigid divisors, etc. And if you've tried to do this kind of thing, you know that most of these steps, you can write out on paper what you want to do and do some sequence chasing or something, but it does not scale well. You cannot go up to large Hodge numbers with pencil and paper, absent some massive developments. Okay, so that's enough about the technology. We can talk about it afterward if you're curious. So far, where have we left the superpotential? We have a flux superpotential that's a small number, and the complex structure moduli are stabilized, but the kilomoduli are not stabilized. We want to establish that the superpotential is the thing above plus a series of instanton terms, now Euclidean free branes that can stabilize the kilomoduli. Here, CD is a dual Coxeter number of a confining gauge group. For Euclidean free brane, it would just be the number 1. And AD is some Pfaffian that encodes dependence on complex structure moduli in the axial dilaton. Well, we're going to need to stabilize H11 kilomoduli, we're going to need at least H1 of the Pfaffians to be non-zero. But the trouble is there's some functions. And so if you don't exactly know where you're going to land in the moduli space, it's hard to ensure that they're non-zero. So we're going to require something stronger. We're going to require that the Pfaffians are not actually functions, rather that they are numbers. So how do we do that? So let's think about some divisor D in a Calabi-Yau threefold X and its uplift D hat to F theory. Then Wynne showed us that smooth rigid divisors D hat contribute to W. That is to say, the fermion zero mode counting tells one that the Pfaffians are not identically zero for a divisor obeying those conditions. And by rigid, I mean that this vector of sheaf homology dimensions is 1, 0, 0, 0. That means it doesn't have any normal bundle deformations in particular. So the divisor is just one fixed rigid thing that just sits there. Those sorts of things support superpotential terms. But the Pfaffian is generally a section of a bundle over the moduli space, and not one that is easy to compute. I don't mean that the computation is a challenging one, but one could do it slowly. I certainly don't know how, and I haven't seen other people show how to compute it in any kind of generality. But if the divisor has what's called a trivial intermediate Jacobian, then the Pfaffian is a section of the trivial bundle over the moduli space. The intermediate Jacobian is just this thing, H3 of D hat R over H3 of D hat Z. So it's some torus-like thing. And if that intermediate Jacobian is trivial, then the Pfaffian is a section of the trivial bundle over the moduli space. And then the Pfaffian is just a Pfaffian number. That simplifies our analysis considerably. I should stress this is not essential. You could perfectly well have said, I'm going to evaluate AD of Z tau on the expectation value of the complex structure moduli and the axiodilaton, and generically it'll be some non-zero number. What we were trying to prevent was a conspiracy theory that says that when we find interesting vacua, those occur where the Pfaffians have zeros. If that were to happen, it would invalidate the stabilization of the Killer moduli. So we tried to arrange that that doesn't happen. So what we need to do is we need to find smooth, rigid divisors with trivial intermediate Jacobi. That means we have to, yes, Edward.
Is there a numerical value of a Pfaffian that's important to calculate?
Yeah, thank you. It would be lovely. When we began this work, well, in fact, at intermediate stages of the work, let's say as late as June of this year, we were not sure whether a modest change in the numerical value could be disastrous. When we went through it, it became clear that actually a change in the value of the Pfaffian causes an effect that's suppressed by 1 over log W naught. So at the large W naughts where we're working, there's no effect. We checked this explicitly by taking the Pfaffian numbers to be between 10 to the -4 and 10 to the +4, and had no changes. The vacua always persisted. Now we could, we could scale a little bit above 10. It's not that they die at 10 to the 5 either. Alexandrov, Sen, and Stefanski have computed almost this, just not quite in this setting yet, and I anticipate they might be there soon. But bottom line is we don't think the numbers actually matter as long as they're in a relatively reasonable range.
Okay, thanks.
Other questions? Okay, so we need to find rigid parametric divisors. This again is actually a challenging computational problem. The only way that we could see that would be feasible is to find a combinatorial formula for the Hodge numbers. So my student Nanki Kim did that and found a combinatorial formula in the style of Badirev by stratification, which means breaking the toric variety into little pieces and computing and then adding those up. So that's a group who carried out a search, and I won't bore you with the details of the search, and we succeeded. We found lots of examples. What I will tell you about is some of the properties of those examples and the vacuum structure. Okay, so this is the entirety of the story of the stabilization of the Kähler moduli at the level of the superpotential. Just a remark for people who've been thinking about this. If this is something you've looked at, you might have thought maybe, is it common that there are enough rigid divisors? At small h11, it's not that common, but at large h11, it is very common indeed, and it's not a very serious cut on our constructions for there to be enough rigid divisors. So that's just an observational fact. We can explain the fact too.
So these divisors are D3s in a Calabi-Yau?
Correct. Yeah. These are divisors. Divisor D is a 4-cycle in X. The Calabi-Yau threefold is wrapped by Euclidean D3 branes, or D hat is wrapped by Euclidean M5 branes. What was that the question?
Well, that's me.
Yeah. Good. Other questions? Right. So just one more technical remark. We found it convenient to look for so-called prime toric divisors, that is to say, divisors associated with the vanishing of the toric coordinates. Those are easy to get. They're always smooth, and so life was easy. Okay, so at this point, we've found lots of examples in which the superpotential takes the forms. We've proved, I claim, that the superpotential takes the KKLT form, an exponentially small number plus a sum of at least h11, things like this, where this is some non-zero number, and that's an exponential. It remains to see whether that thing has a supersymmetric minimum inside the moduli space. That's not obvious. And in particular, so you want to solve this condition, right? The F-flatness condition for the Kähler moduli. And well, you easily see that means that the vectors of the Kähler moduli have to be proportional to log of 1 over W naught, where a Kähler modulus associated with an ED3 has a coefficient 1 here. And if we're talking about an SO8 stack of 7 branes, it'll have coefficient 6. But basically, they all have the same size up to a factor 6. So one needs to ask, is there a point like that inside the Kähler moduli? So where is it? Well, so here's a picture of the Kähler cone in a threefold with large h11. Each little polygon is a Kähler cone associated with a particular triangulation of the parent toric variety. And all of these are different triangulations in which different curves have positive volume. You go through from one little triangle to another one, you're going through a flow. And the problem is, you start out somewhere, shows up. start out somewhere like the white dot over there, and it turns out the SUSY vacuum is, let's say, over there, and you have to walk through exponentially many chambers. Luckily, we found an algorithm that can just take a bearing toward the solution and walk there through all of this. And along the line, you only encounter polynomially many different chambers. But if you were to try to throw darts, it's completely hopeless. Okay, so then you find the supersymmetric vacuum. Now, the question is, do we believe the supersymmetric vacuum? I think the superpotential is under outstanding control. I don't see any problems there. We've ensured that the Pfaffian numbers are non-zero by standard zero mode counting, and that if the numbers fall in a particularly large range, the solution persists. And this is the remark I was making about the shift in the VEVs as one changes the Pfaffian numbers. So this is very robust against changing the Pfaffians. So not a problem there. We can show quite directly, because we know the other effective divisors, that Euclidean D3 on other divisors are negligible. That's provable. And also Euclidean D-1 branes are negligible because G string is small. I mean, one has to worry about exactly the exponent, but remember my exponents were 7/28, not 1. And this one starts at 1. So that's under control too. Okay, but that was the easy part. We controlled the superpotential. And so, we could have, I guess, finished here and said, we've exhibited compactifications in which the superpotential takes the KKLT form. But let's see if we can understand the Kähler potential too. So now, as Nima asked, how big are these cycles? The Einstein frame volumes are pretty big. They go like log 1 over W naught, and W naught is 10 to the minus 62. But the string frame volumes, well, frustratingly, G string goes like 1 over log 1 over W naught. And so that exactly cancels the parametric growth. Let me repeat that. As W naught gets smaller and smaller, if I find vacua with W naught closer and closer to 0, the Einstein frame volumes grow without bound. But the string coupling shrinks. And in exactly such a way that G string times Einstein frame volumes are constant. So there's no parametric growth in any control parameter of the string frame volume. So then you wonder, how bad is it? But there's hope, because we're at weak string coupling, right? G string is small. It's 10 to the minus 2 in this example and smaller in other examples. And so we actually understand a lot of things at string tree level. And then we have small corrections away from string tree level. So what we can do is we can study the Kähler potential to all orders in alpha prime and at string tree level, and then systematically incorporate corrections away from string tree level. The Kähler potential takes a form like this. Normally it would be minus 2 log of just the simple classical volume, but instead one has an expression like this. There's a loop correction, and then an infinite series of polylogarithms in e to the minus 2 pi t's. So now, previously I showed you Worldsheet instantons, I called them Worldsheet instantons, but okay, e to the 2 pi iz type things. These are on X, not X tilde. These are actual Worldsheet instanton corrections to the Kähler moduli space of X. So these curves are in 113 dimensional rather than 5 dimensional moduli space. B here is the B field. Q is a class in the Mori cone of X, and Q are the GV invariants. And here I've written the good Kähler coordinates as well. Okay, so this is at string tree level. So now how good is this? We should ask how well the Worldsheet instanton sum converges, right? Because look, I mean, I have some tidy looking expression in terms of some polylogs, but is it actually a controlled expression? In particular, what's the radius of convergence of that expansion inside the Kähler moduli space? That's the question. So let me define a control parameter C, which is for a number n, which is a counting number. Cn is the GV invariant of n times a curve class, e to the minus 2 pi n times curve class dot vector of Kähler parameters. So if you pick a direction in the Mori cone, Q, and you start going out to Q, 2Q, 3Q, and calculate the Worldsheet instanton terms at Q, 2Q, 3Q, you'll be seeing these objects. So this is telling you how the Worldsheet instanton expansion behaves as you move out along a fixed curve Q in the Mori cone. And the thing converges if the Cn's go to 0 as n goes to infinity. Right? We want, as we study higher and higher degree curves, further and further out in the homology lattice, we want to have smaller and smaller corrections. So we just compute the GV invariance and check. And for small curves, I don't mean small degree curves, I mean small volume curves. We try and find all the small volume curves because T shows up here. If you pick a curve class that has a large dot product with the Kähler moduli, then it's totally negligible anyway, and you don't need to be afraid of it. So we're worried about small curves. But there's two kinds of curves. Curves that I'll call nilpotent. A nilpotent curve is defined as a curve where there exists some number k such that for all, there exists some number k max such that for all k bigger than k max, the GV invariant along that direction is 0. Namely, pick a ray in the homology lattice, and if at a certain point along the ray you start getting only 0 for the GV invariant all the way out, that ray is nilpotent. And then the opposite of that is potent. So there are potent ones where the GV invariants come in infinite series. Well, clearly the nilpotent ones are not completely disastrous because at a certain point the series terminates. And so we just explicitly incorporate them. We include them in our calculation. I want to show you, but we put them in, they give sub% level corrections. After all, on the previous slide, I was showing that the curves show up in terms of some polylogs. Nilpotent curves give finitely many polylogs, and you can just evaluate them and put them in. But potent rays, you might be more worried about those. So what we do is we keep searching. This actually was the only part of the computation that needed a cluster to do it. We searched pretty far out in the worry cone, which now is 113 dimensional. In this example, 214 dimensional in our hardest example, until we found a lot of potent curves. Okay, we found 1728 before we got bored. And let's think about some potent curve. Okay, so I have some curve class C in h lower 2 of x, z. And we're going to consider the GV invariance along multiples of the curve. So here's an example. You get 3 minus 6, blah, blah, blah. And these things are growing. And then you go out to 100 and it's something like that. Now I'm proud of this result because as far as I understand it, although these things can be calculated extraordinarily well in non-compact cases, I am not aware of any methods for computing GV invariance to relatively high degrees in compact models with more than a handful of Caleb moduli. Here we have 113, and we can just go out to, degree 100 if we want to. Why are we looking at that one at 100? Because we can see that there's an exponential increase with a very stable rate. So the GV invariants are increasing exponentially, but on the other hand, e to the minus 2 pi n is decaying exponentially with n. And so the question is, who wins? Well, there exists a t for which the Kähler moduli suppression wins, and there exists a t for which it doesn't. That's the radius of convergence. Now, an example that was encouraging to us early on is the quintic. Okay, think about the quintic. You know the GV invariant for the first curve class in the quintic, it's 2875. And if you just take that one and use that to estimate the radius of convergence, you estimate the radius of convergence of the Worldsheet instanton expansion is 1.27. And Cornell showed exactly it's 1.208. So actually, leading ones aren't so bad. We didn't do leading ones, we went a long ways out to check really low. But this just shows that exact things can be well matched by these low order expansions. And so the question is, in our vacua, is T large enough? And it is. Here's a plot. This is log of the control parameter C, which you want to be decreasing with n. Here's n. And all the lines, I call your attention to the fact that they're all straight lines with negative slope. That means that the GV invariants are very cleanly exponential, and they're all cleanly exponential in such a way that this suppression wins over that growth. This histogram is showing you that we didn't just miss the ones that have flat or positive slope. There's a huge pileup around here. There's tons of arrays like this, but we just could not find any in there. I can't prove there aren't any, but we could not find any arrays with positive slope. So we think the Worldsheet instanton sum is very well converging here. Okay, so let me just flash the details of this example, and then I'll comment briefly on what you might think about the CC or computability in this context, and then I'll close. So here's the actual details of the example. Here's the polytope in question. The polytope is a polytope in z to the 4th. So the columns are the coordinates of the vertices. So you can see where all the vertices are. And in this geometry, there's 25 SO8 stacks and 89 Euclidean 3-branes. All of them have trivial intermediate Jacobian. With this choice of fluxes, I showed you before what the superpotential is. So just 729s and 728s. And that stabilizes the moduli here. And we find then a supersymmetric ADS4 vacuum with vacuum energy minus 10 to the minus 144. Planck to the 4th. And for this example, we're sort of living off of 2 over 252 to the 58. That's from W squared, plus an additional suppression from the Kähler potential that takes you all the way down to minus 144. So as I quoted before, the cycles are pretty decently sized in Einstein frame, but in string frame, not so decent. But on the other hand, here's the demonstration that we're not killed by Worldsheet instantons, let alone by anything else. So I think it's sort of fun to think about how this compares with a Bousso-Polchinski type picture. So let's step back. You would expect to find a vacuum with vacuum energy 10 to the minus n, you might have to search through of order 10 to the n vacua. But we have H21 as of order 5, examples of 5, 113 is the one I showed you. And so our flux landscape is low dimension. So also large H1 is not essential, it's an accident of the Kreutzer-Skarka list. So we're not living off of that. And so why then can we succeed at all at finding small rho vacuum, let alone why can we succeed quickly without paying an exponential cost? And the reason is the following: in an n-dimensional Bousso-Polchinski landscape, just sort of a cartoon for how the flux scalar potential should look. One thinks about the vacuum energy as being minus a big number, plus a vector of quantized fluxes, another copy of the vector, in some quadratic form. This is, I stress, just a model of how one can think about it. Then the picture is, if you pick a flux vector in z to the n such that its length squared measured by the metric determined by Cij is almost exactly plus lambda to the fourth, then you get a very small vacuum energy. That's the game. Right? We are not playing that game. Rather, we've made all the perturbative terms, perturbative things like this, be 0 by choice of flux quanta. And so the superpotential is purely non-perturbative. It's non-perturbative in the sense that it has what I was calling two-way Worldsheet instantons, and literal instantons, Euclidean D3 branes. And that's all there is, no classical part. And so since this is the superpotential, with no order 1 terms, well, of course it makes sense that if you're balancing two exponentials against each other, you can get something that's exponentially small. At the level of effort, I would like to think of this as a polynomial effort in tuning integers that allows an exponential hierarchy. Right, because I just needed to, I mean, indeed, 729s and 728s are very close, but I didn't have to search through exponentially many geometries and fluxes before I found them. I only had to search on a laptop for a little while before I found it. And then the exponent does the work for me.
After all, because you have supersymmetry, you could also get 0 vacuum energy with not much problem.
Yeah, and exactly. And so that's exactly what we're doing. It's spontaneously breaking supersymmetry. Precisely. Now, I should say, although this is a lot easier than it might have been, we did have to do a certain amount of hard work. We had to be able to do all these things listed here on a very large scale in a topologically complex realm, but we can do those things with CY tools. And so with those data in hand, we can do a polynomial amount of work and find exponentially small.
CY tools? Sorry.
CY tools is a software package, Calabi-Yau tools that we have written and released.
Oh, you've written them.
Yeah. My students, Mehmet Demirtas, Andres Rios Toscon, and I, although they actually wrote it, but I'm involved. But anyway, they wrote the code. You can get it if you want. It does all these things, but soon we will release. Okay, let me not say soon. In time, when we're sure that it's stable, we will release a version that will also compute GV invariants, construct orientifolds. It has a function, find KKLT vacuum. Just press find KKLT vacuum, and it gives you a vacuum. So that is not well tested yet, but it does produce these solutions. And the final answers are expressed in terms of integers. I mean, if you think back to that page where I was showing you all the details, I specified everything one needs to know, not quite the triangulation. Okay, we could also list that. You can also go to the archive, auxiliary data, ancillary data for our paper, and download all of the integer information needed to specify these solutions and check them yourself. Okay, so let me conclude. We've given explicit constructions of supersymmetric ADS for vacua in orientifolds with H21 not too big and H11 pretty big. I didn't show you all of them. We have some at 51, 113, 204. The stabilization is a weak string coupling. It's a large complex structure, large Einstein frame volume. We've subjected these to some pretty severe tests. We judge them to be robust, and they're incarnations of the KKLT scenario. So the main finding is that supersymmetric KKLT vacua are part of the landscape. So we can construct them, we can manufacture them. The mechanism we used for small W naught led to exponentially small vacuum energy. And because the search is automated, large-scale studies are possible, one can do a lot more things. The uplift to de Sitter is a very interesting question for the future. Thanks so much.
have a question if people can hear me. Yeah, can people hear me on Zoom? Yeah, okay. So I think you answered this, but I think it was a little too quick for me. In your Racetrack superpotential, so that translates into a coupling between fields. This coupling presumably also receives corrections from d instantons, which are suppressed by the same factor of e to the 2 pi tau.
Yes.
So I think you mentioned that somehow these are suppressed so that they don't affect the shape of the superpotential, but
yeah,
can you
right.
just repeat that?
Thank you. It's just by this. It's that those things so Euclidean d-1 branes do contribute, okay, a potential in the tau direction. But they go like e to the 2 pi I tau, e to the 4 pi I tau, etc. And this is the 7/29ths or 7/28ths root of that. So the leading Euclidean d-1 is more suppressed. That's why these ones are safe. Now, one could have asked, well, what about Euclidean d3s? That is the reason that we ensured that the divisors had constant intermediate Jacobian, because otherwise the fact that the Pfaffians AB depend on the complex structure moduli and the dilaton would mean that once we stabilize the Kähler moduli, these terms, the ED3s, would introduce a new pull on the axiodilaton and possibly mess with things. Not necessarily fatally, but they would do it in a way that would be hard to compute. But both of those effects are absent. Another question?
Well, my question is just what Juan was asking you before. As far as I understand, this story about Worldsheet instantons is computing periods of the homomorphic 3 form.
True.
And it's clear that just classically computing that directly isn't easier, or is it effectively what you did because that's how you computed the GV invariance?
That's how we computed the GV invariance. Yes, yes. So right, all of this is a sort of a computational approach to mirror symmetry and toric varieties. So that's the driver behind the calculations is actually just computing the periods in the following way. You find the fundamental period, you find the full Picard-Fuchs system, you express them in an integral basis, and then you can read off the GV invariance. Did that address the question?
Yes.
Yeah, I still would like to understand geometrically the first step, the perturbative part of the potential a little bit more.
Right.
So maybe if you could go to the slide. So you had sort of basically the statement that this W perturbative was equal to 0 for any value of tau. At least it had this line of zeros. And at the same time, it's also minimized, at least by the Kähler moduli. Is that correct?
Yeah, sorry,
by the complex
share
structure.
screen
Sorry.
here. I apologize about that. So in attempting to navigate back to here. So
yeah, and maybe it's the next slide, but
right. So here we are. So right. So one thing I didn't fully explain is how exactly do we pick? The idea was to pick fluxes for which the perturbative thing vanishes, but how can you do that?
yeah, but also because if it's minimized by the relative to the Kähler, to the complex structure moduli, that equation is that your flux is an anti-self-dual.
Imaginary self-dual.
Imaginary self-dual. But since it's true for any value of tau, at least according to your story,
yeah,
which means that both the H flux and the F flux both are imaginary self-dual.
Yeah. It means that H is equal to G string times F, times with a star.
Right, but since it's true for any G string, because you have the line of zeros, and you say it's a line of minima.
Yeah.
So it's true both for F3 and H3 that they're anti-self-dual. Imaginary self-dual. So I'm trying to understand that geometrically, how it's possible to have two independent fluxes that are both imaginary self-dual.
Well, the statement is only that the deviation from is that the scalar potential vanishes identically along that direction.
Yeah, but shouldn't we also have minimized with respect to the other complex structure moduli?
All of the ones transverse to that direction, yes.
Right.
But then there's one direction left that hasn't shown up.
But how do I know that you've minimized? I still don't see where you did that step.
I didn't show you that step. What one had to do is, so how did I find when I showed you this vector P here? We find fluxes such that. So what is this such that really? What you have to do is you have to find a vector of fluxes such that, not in terms of this F and H, but in terms of what you might call M and K and usual KS type framing of things. You have to find a vector P that lies in the Taylor cone of the mirror that has a 0 dot product with the vector K.
Right, both with F and with H.
Yeah, and that's the condition that ensures that you actually have a perturbatively flat direction. So that's a non-trivial condition on integers, but for which solutions exist.
Thank you.
So as far as I understood, there's 2 ingredients. One of them is to find an instance in which the superpotential has a perturbative flat direction, and the other one is for the racetrack condition.
True.
Which one's the harder one to find? On the first one, is it easy to then satisfy the racetrack condition?
It's not completely trivial, but we didn't spend an enormous amount of extra time, or we didn't spend disproportionately more time paying for a statistical cost on any step of this chain. So what do? You in terms of a manufacture process, you want to pick a Calabi-Yau for which you can do the orientifold, where you have enough rigid divisors. The rigid divisors have constant Pfaffians. You do that. Those are some cuts, but they're not impossible cuts. And then you try and find a perturbatively flat direction. And that's a demand for sure, but that's a demand on the fluxes too. So once you fix a Calabi-Yau, now you start picking flux until you find a perturbatively flat vacuum. And then it's about, I would say, very roughly equally hard then to find a perturbatively flat vacuum that has a decent racetrack. However, when we just run our code, you get lots of solutions, just tons of solutions with W0 10 to the minus 5, 10 to the minus 10, 10 to the minus 20. Those just come boiling in. I haven't shown you any of those because we wanted to absolutely lock down as much as possible all of the control questions. And those control questions go in log W0. So we just pushed it to the limit to find the smallest ones that we could in this context. Actually, I found smaller W0s than I have shown you. The smallest one we found, 10 to the minus 95, was in a case where the Kähler moduli space was 214 dimensional. We could still compute GV invariance there and study this rainbow plot of Worldsheet instanton convergence, but we judged the evidence there to be less convincing because we could only compute a modest number of terms. So we sort of were balancing control. So what I've shown you are the best ones we had in the summer anyway, in terms of control. But what ones are typical? Oh, W0 10 to the minus 5, 10 to the minus 10, they are everywhere. And then you're not paying much of a price. Here we had a 7/28, 7/29 racetrack. But we had racetracks like 34 2/80ths and 35 2/80ths. And things like that take a little while to look for in general. What you need is a big hierarchy in GV invariance and a clever choice of fluxes, but we know how to do this.
Something maybe a little closer to the way Bousso-Polchinski works. And I guess I'm sure Douglas and Bennett and people talked about these things a long time ago. So to be honest, imagine you just had just one Z, one Z, and superpotential is, I don't know, Z cubed minus Z or something like that. So I have 2 vacuums. Now imagine I have 10 of those guys decoupled. I have 2 to the n vacuum. And then they're all coupled up. You can sort of count. But anyway, it has nothing to do with the exponentially small superpotentials or anything. But just the fact that you have a lot of these Zs should give you 2 to the n, 3 to the n, some number of that or like that.
Yeah.
And then you might have to, anyway, there's some details. You want to make sure that the W's aren't scanning around some kind of big value, that they sort of scan around 0, but maybe you're in the neighborhood of having some kind of R symmetry or something like that. Are those things, I mean, have you guys thought about certain things like that too? Are they, why are these, I mean, anyway, obvious question.
Right. It's in fact how we started doing it. So what we first started doing was taking integer choices of, once we had the capability to compute all of these pieces, setting aside the perturbatively flat vacuum, but just to compute the flux superpotential, et cetera, we started looking for vacua as you described. Pick some fluxes, see what you get. And then what we thought, which I still think is right, is if you want to find something 10 to the minus n, you're probably going to have to try order 10 to the n per diagonals. Okay, so we thought let's find something where W naught is 10 to the minus 3 or something like that. Sure, one could do that. I think we could do it right now, but you're never going to dig very deep that way. And the things that we found, there's a nice continuous flux approximation distribution for the values of W naught that Denef and Douglas and Ashram and Douglas worked out.
No, but you're not gonna, I mean, it's gonna be hard to find tiny ones, but those are going to be a bigger relevance to like describing the world, right? We don't want to start with we don't want to start with something which is like such a minuscule supersymmetric CC.
True. We won by putting all the scales down, so that means we cannot be finally victorious, right? We cannot also really solve the CC problem with this set.
I guess I had a question that I could ask about what you've actually, but maybe I could also ask about the other case. Looked at it a bit. It would be interesting to see if the sort of distribution type questions and all the things that we naively assume. Well, for example, in the case we just talked about, we basically assume that the W naught is around when it's small, it's basically smoothly, uniformly distributed, so on and so forth. Is it actually true? Or is there any structure? So that's the sort of thing that even if you could only dig down to W naught of 10 to the minus 3, it would still be sort of interesting to see if there's any structure.
Honestly, that's what we were thinking of doing this spring, this past spring. But then we found that these things were working, and we thought, well, these things we
maybe I can ask the analog question here. So in this kind of setup, you might again roughly think that it's log W naught that's that's uniformly distributed and so on. Is that basically true?
Yeah. Exactly.
What happens with the Calabi-Yau when you go along this direction? Are you approaching a
good.
manifold form?
Yeah, the reason, so this direction does not, to the best of my knowledge, take you to a very exotic place in the complex structure moduli space, but the killer moduli stabilization takes you to a place where the overall volume is quite big compared to the 4-cycle volumes. So if you remember the numbers I quoted at the end, the 4 cycles wrapped by ED3s have volume about 20. And the whole 6 manifold has volume 10 to the 5, which is not in the usual 2/3 power relationship that one would expect if we're just an isotropic space. And so what's happening is they're big, size 20, but then a much bigger space. And so that's where you're pushed to. And those hierarchies are coming from the large H11 as far as I can understand it. When H11 is big, there's so many little curves, so many curves. The Morricone conditions are many. And so if you tried to make all the curves big, the whole space would be just gigantic. And so some curves are pretty small. That's why at the end, I said there's a whole bunch of nilpotent curves that the GV series terminates that give finite corrections. In this example, there was 238 such curves, all of which gave some dialogue, and we added them all up. So, we were near 238 different constants in that sense.
If there are no more questions, then we can just thank Liam again.